Okay, great. So thank you very much for this introduction. And so how much time do I have again?
Yeah, let me
I
check. I
forgot.
think it's around half an hour.
Half an hour. Okay, I'll try to keep it to half an hour. I might not be able to present everything, but that's okay. So I just wanted to give some overview of the research we're doing in my group, and I will focus more on the bio-derived materials because this is the scope of the journal. So I would like to start by showing this graph, which represents the path to net zero by 2050 for the UK. I know that China has now committed also to reach net zero by 2050, but in China it might be even more challenging than here because it's such a large country and there's so much coal. But basically, the scenario in the UK shows that if we don't change um, something now and accelerate rapidly the technologies, the sustainable energy technologies, we won't get to net zero actually by 2050. In fact, if you see this dot here, these were the initial targets of the UK, which were 80% reductions in CO2 emissions. And then, as you probably know, UK was the first country to commit to net zero. But as you see, if we do business as usual and we go by the current implemented politics, we're not going to even reach 80%. So the conclusion here is that we need to really accelerate the implementation, development, and uptake of sustainable energy technologies. And so, if we look at the CO2 emissions, this is where we were in 2019. So, although this have been decreased since the Industrial Revolution steadily, they're still quite high. And of course, the UK has very ambitious plan, as I said, to really go to net zero by 2050. And a way you have to do this is that you need to decarbonize the economy across all sectors. So not only transport or not only power, you need to look across everything, including shipping, transportation, power, buildings, waste, industry, aviation, and also uh, land use and agriculture as well. So this will be done by a huge increase in the renewable energy. And so again, this is where we are today. And as you could see, there's already quite a big fraction coming from renewables, but this is not enough. And these are two illustrative mix of how the energy generation in the UK might look like in 2050. And you see that actually both of these scenarios have significant amounts of renewables. In the UK, this renewable energy would be mostly generated by wind, and there's a little bit of nuclear in the mix and a little bit of gas. And hydrogen also is likely to play a major role in a future green economy. So the good news is that it looks like we're gonna have a lot of renewable energy available, and this is gonna be cheap in the future. And so we need now to develop a lot of technologies to enable the use of this renewable energy and electrify as much as possible. But not only electrification is the solution. So as you could see here on the screen, we will have a mixture of things available to us. So, we'll have renewable energy that we could potentially store in batteries and use for the grid. But also, as you know, batteries are great enablers for road and public transportations. Um, and then as we then still gonna have a lot of CO2 captured from the atmosphere, in particular if we want to generate fast hydrogen. At the beginning, this hydrogen will need to be blue hydrogen, means they still produce from gas reforming with CO2, and we can capture this CO2 and then convert it either via electro or photoelectrolysis or thermal catalysis into chemicals and materials of the future. And then, of course, we have water available, and we could then use the same techniques, electrolysis or photoelectrolysis, to actually generate hydrogen from water splitting, green hydrogen via electrolysis. We also have nitrogen that ideally we could also directly reduce to ammonia. And if we do this, we would feed into decentralized production of fertilizers, which means that we will reduce CO2 emissions from the Haber-Bosch process, which currently generates about 1% of the global CO2 emissions. We're also going to have potentially on-demand maritime transport. Now, as I said, we're going to have hydrogen available initially from syngas with CO2, but then in the future, hopefully green hydrogen from electrolysis. And with this hydrogen, we could actually store it. It's not very clear what the best solution for storage it is. And then we could use it, for example, for fuel cells to generate power. And these fuel cells are also ideal to power more road and heavy duty transport such as trucks and trains. And also this hydrogen could be combined with CO2 to create potentially jet fuels for aviation. So these are just a few solutions to really decarbonize the economy across different sectors. And there's not going to be only one solution. We need to have available many different solutions. And so this is good news. We are all working on these things, but yet we still need to solve a major trilemma here, which is, right, we want all these new sustainable technologies to be efficient and also low cost. We want zero carbon ideally, but do we have enough security of supply? In particular, do we have enough sustainable materials to implement in these new technologies? Because if your materials are not net zero, then you'll never get to net zero. And the production and security of supply is quite important for the sustainability of these technologies, for their costs, and as well as for their availability for the next generations. Now, the issue is that most materials that work very well in the sustainable energy technologies are on the list of critical materials according to the EU. This is the list of critical materials. As you see, the EU is doing that since 2018 and is currently updated it. The last was in 2020, and actually in 2020, lithium has been added on the list of critical materials. So everything you see here in kind of yellow, orange, or different shades of red are critical materials, and they've been listed around the years. And this list is constantly updated, so I guess we will see another one possibly in 2023 or so, and we will see which element will make it on the list of critical materials. Potentially nickel, but we'll have to see. I will get there in a bit. So as I said, all these materials are used in critical technologies, such as, for example, the permanent magnets that are used in wind turbines. This contain all this rare earth like dysprosium, praseodymium, europium, terbium, yttrium, and so on. And then, of course, we all know lithium-ion batteries. And lithium-ion batteries have cobalt in the cathode, graphite in the anode, and lithium itself in the electrolyte. And all these three materials are on the list of critical elements. Similar, if we want to do electrolysis to generate green hydrogen, and if we want to use this green hydrogen in fuel cells, we need to rely on these platinum group metals. And these are very scarce elements. And also, if we think solar panels, we need silicon, high-grade silicon, for which you need hydrogen. And this is also on the critical list of materials. Silicon, I mean, tellurium, indium, all of these are endangered elements. And not only that these materials are critical because of their increasingly economical importance, but also you guys in China, you're very lucky and you have a lot of resources. But if we look back in Europe and in particular in the UK, there's almost nothing. And so we are really dependent on countries like China, or for example, the Democratic Republic of Congo for the supply of cobalt, or South Africa for the supply of platinum group metals because there's nothing here. So of course this means complicated geopolitics, and it's never easy to trade these elements. And so what is the solution? And so that's what we are doing in my research group. We're trying to come up with alternatives to these critical materials. We're trying to design materials that would work equally good or even better than critical materials, but would be based on locally sourced and available precursors, such as, for example, biomass. There's about 26 million tons of biomass produced in the UK per year, and that includes food waste and all sorts of bio-derived waste, agricultural waste. So why don't we do similar to petroleum refinery, a biomass refinery where we could actually extract very defined molecules from biomass, and this could be, of course, cellulose, hemicellulose, lignin, and a lot of other nice things. You could extract natural dyes, chitins, even inorganics from biomass if you want. And so then you can try to use these raw materials that are very pure, because if you use biomass directly, you may end up with a lot of irreproducibility because of the variety. But if you use sustainable extraction techniques to extract these materials from waste, then you could have a reliable source of precursors for bio-inspired advanced materials. And I will talk a little bit on how we do this. We use different techniques, and then you could apply these bio-inspired functional materials to decarbonize the energy, as I said, across sectors, from power to transport to buildings to agriculture and industry and so on. So one way we do the production of these sustainable materials is actually this technique called hydrothermal carbonization. And this is a technique where you take, as I said, precursors from this biomass. You could also use raw biomass, but again, it's more complicated because of the variability from species to species. But in principle, for this process, the carbohydrate fraction of biomass works very well. So the glucose, the cellulose, the chitosan, chitin, everything that is a sugar, everything that is bad for you and you're not supposed to eat it, according to the new diets that you need to eat more protein. So we could actually use the sugars to form these carbon materials. And you do this in water. So it's a bit like a sol gel process of carbon materials. And because you have this solution-based process, you can actually nicely control the properties of the material. So you could actually tailor the porosity, the surface group, the morphology, according to the application you want. So it's a little bit different than just baking, normally taking a precursor, putting it in a furnace, and not really knowing what properties you're going to get. Here you can actually tailor it depending on an application. Now, this technique gives you three things at the same time. Because it takes place in water, after a few hours at around 200 degrees, the sugar will start forming a black precipitate that you will see at the bottom of your autoclave, and you can filter this out, and these are the formation of these nice carbon materials with different morphologies. Now, everything happens in water, so basically once you filter this black stuff out, you end up with an aqueous phase. This aqueous phase contains actually two types of products. One are the derived chemicals that are in the aqueous phase, and if you do an HPLC, you would find sometimes a bit of HMF, but not much, because mostly this is converted to these carbonaceous materials. But you can find very important chemicals such as lactic acid or levulinic acid or formic acid and formates in the water phase. And so you could use then some sort of separation, and you could use this as bioprecursor for further development of other chemicals. And also you will find some very interesting nano materials that have fluorescent properties. These are known in the literature under the name of carbon dots. However, depending on how you make it and from what you make them, they appear very different. And these have also potential to replace the classical inorganic carbon dots, but also have a new class of fluorescent materials that are sustainably made. So you could use them in photocatalysis or as fluorescence tag in bioapplications. Now, a little bit more on how this hydrothermal carbonization works. As I said, it's a solution-based process. So, for example, if you start with glucose, you're gonna isomerize that glucose to fructose, and then because of the conditions where you're working, so you work around 200 degrees, around 30 bars, these are subcritical conditions, so you're going to dehydrate the glucose to hydroxymethylfurfural. This hydroxymethylfurfural can actually rehydrate in equilibrium because it's in the autoclave in the water phase to form levulinic and formic acid, but also it can polymerize to form these black precipitates. And this happens via multiple types of reaction, Diels-Alder, self-condensation, or also aldol condensation with hydroxyacetone. They also form in situ during this process. And there is this condensation reactions and then some intermolecular dehydration that lead to the formation of this spherical black carbon particles at the end of your reaction. And as you could see, you would have first a nucleation. So once this HMF is formed and starts, let's say, polymerizing via these reactions, you form some nuclei. This nuclei will continue to grow the more HMF is depleted and added to this until you reach the final size of your particles. So in hydrothermal carbonization, you always get these nicely spherical particles that are normally non-porous. I can even control their pore size distribution by playing around with the reaction conditions in the autoclaves. And of course, if you use other materials chemistry tricks such as soft templating or hard templating or other templates in the synthesis, you could play around and produce a wide range of porous carbon materials that you could design with whatever porosity you want. You could do them coral-like structure. For example, here we use some latex nanoparticles for templating, or you could do hollow spheres. Again, if you use, again, latex nanoparticles, but just coat a very thin layer of carbon around each latex and then remove the latex. Or you could make a hierarchically porous material if you do an emulsion phase separation process, or you could add a block of polymer and get this really nicely ordered carbons and so on. So, you know, the possibilities are numerous here. And also you could combine this hydrothermal synthesis of carbons with the inorganic hydrothermal synthesis that is very well known for a long time and produce these really nice hybrid materials. And these are some platinum on carbon. This is one single platinum in a hollow sphere. These are some tin oxide carbon composites and so on and so forth. Now I want also to talk a little bit about the carbon dots that I said you will also find in the aqueous phase once you actually do some dialysis and centrifugation. So as you see, these carbon spheres, the big guys that I just showed you before. And then if you look very careful here, there's some sort of layers formed, and on these layers you would identify this crystalline carbon dots that obviously are forming from an amorphous phase, but then they do appear to be crystalline or at least partially crystalline. They have a very complicated structure that we haven't really quite got to the bottom of it. There's some fraction that are more amorphous, but there's clearly some fraction that are very crystalline. And it's actually very difficult to analyze the structure of these materials because, you know, they are so tiny that you can't really do XRD with other other diffraction techniques. So you rely a lot on electron microscopy. I am still to find the best collaborator to help me in this area. And just to say that we make these dots, but it's very nice because you could also tune their fluorescent properties. So as you make them, you could either oxidize them, meaning that you put more functional groups on the surface, or reduce them. And you would see that if you reduce them with a reducing agent, you see more graphitic domains, and you almost eliminate all the surface groups. And we've characterized them thoroughly, and this is just um, a summary that basically, as you make them, you have some sp2 and sp3 stacking, and you have some oxygen groups, you have less carboxylic groups, and you have some more aggregation. And actually, once you oxidize them, they become more amorphous. You really increase the fraction of functional groups, in particular carbonyl, and you will, of course, have less pi-pi stackings. You'll have a lot of carboxylic acids, and if you do EPR, you'll see you'll have less radicals here as well. And if you reduce them, then basically you have more graphitic domains, more pi-pi stacking, and you'll have less functional groups. And the fluorescence changes accordingly. So as you see here, we have been looking at the fluorescence, and they display this wavelength dependent fluorescence. And we've also did some transient absorption spectroscopy here, and this is just to show that there is a huge variety between these materials. So as you see, the one they have functional groups, they have a clear peak around here, and also this is smaller for the one as made, because they have less functional groups. And if you take away all the functional groups, basically the excited state absorption shifts on picoscales, and you don't see this clearly resolved peak here at 450 nanometers. So their fluorescence properties are really dependent on their structure, and this is just a cartoon showing you really how the fluorescence is and what is responsible for their fluorescence. And it seems that, of course, for the oxidized one, they have the highest quantum yield and the highest fluorescence, which means that you need some sp2 stacking, but also a lot of oxygen groups here to get the emission from these materials. I will now move to another class of materials from biomass that we're working on, which are based on electrospinning carbon fibers from lignin. So what we do here is we take lignin, we electrospin it, and then we stabilize it and we carbonize it to produce this freestanding carbon fiber mats that we then use in flexible supercapacitors, for example. And here, what I would like to say, when you work with biomass in general, but in particular with lignin, that is very important that you characterize very well your precursors. So we're working with kraft lignin here, both hardwood and softwood, and it's very important to know all this detail: the TG transition temperature, the molecular weight, the polydispersity, the carbohydrate fraction, which you could see is very low, the ash content, which for us is very low, how much sulfur, and so on, because all of these parameters that are in your raw material or raw lignin precursor will affect the properties of the resulting material. So again, you need to do this 2D HSQ NMR, where you can actually quantify the linkages between the lignin. So you know that you have here some more CO linkages, and here you have more CC linkages. And this would be very important about how this carbonizes and which bond is breaking, as well as determining the amount of OH groups on your lignin and determining how much units you have. So hydrophenyl to guanylyl to styrolugenyl, condensed phenolics, and aromatics. These are all very important to know before you actually transform your biomass precursor into materials. And also, we've been looking a lot at understanding what happens during the stabilization of these materials. And you could see here some mass, TGMS, and some NMR, looking really how functional groups and what you get out of this during stabilization. And then you can get some insights on how the stabilization occurs and what is the best temperature. And only then you could get some really nicely controlled carbon fibers that you could make directly from pure kraft lignin, either hardwood and softwood. And you could go and carbonize this, of course, to much higher temperatures to make and render them conductive. We learn how to control the diameter of these fibers as well. So you could make them thicker or you could make them thinner. And you could see in this graph, and you could use X-ray tomography to look at them. And this you could do by adding an oxidant in the solution. So the more oxidant you add, the thinner the fibers, and also the more porosity and the more functional group. So if you're looking for supercapacitor applications, this could be ideal. We also learn how to densify this carbon fiber. So as we make them, we apply some pressure and pack them together. And in this case, because we spin it in sodium hydroxide solution, we form some sodium carbonate during the lignin fiber. And as we compress them, this actually helps to compress them. And you could actually densify them from 0.1, which is very light when you just as make it, to 0.6 gram per centimeter, which is quite a lot of densification here. And you could see and follow again by computer tomography this densification, and you could see that you maintain your porosity, but the pore shape is changing. And if you apply this, for example, in freestanding supercapacitor applications, you would see how actually the volumetric capacity of your lignin fiber compared to the raw fiber increase hugely. And so this is the volumetric energy versus the volumetric powder. This is pristine versus densified. So this is actually quite nice and a nice way to really increase the volumetric energy density of your materials. And we could also make all the carbons from lignin by applying fluoronics and doing this ELISA, evaporation-induced self-assembly. We use glyoxal here as a cross-link, and you get this really nice order porosity from pure lignin that you can transform into all the carbons. So again, we've been working a lot in this area, and we've been publishing also with Chang in ECOMAT. As you could see here, we have a nice review together and a lot of other Wiley journals. And so obviously I won't have time now to go through all these applications because I'm kind of running out of time. But just to say that we are applying our sustainable materials in all these technologies here, batteries or low-cost hydrogen production, platinum-free fuel cells, and also for the carbon dots in photoelectrocatalysis. Maybe I'll just show you one slide on sodium-ion batteries. So we're trying to move away from lithium-ion batteries to more sustainable batteries. So we want actually to design a battery that is both performance, sustainable, and low cost. And one way to do this is actually to move to more sustainable battery chemistries, moving away from lithium. And in my group, we are exploring some that will give you not so high energy density, but actually they're based on abundant elements, and these are ideal for stationary. This is sodium and potassium, and very recently, can you still hear me?
Yes.
Hello. Yeah, because I just got a message there's problems with the network. Anyway, we're also working a bit on aluminum ion batteries, but I just wanted to show you just one slide saying that in sodium ion batteries, we are looking to replace graphite that doesn't work for sodium with these more disordered hard carbon materials by doing this hydrothermal synthesis and a lot of thorough characterization. We go from hydrothermal spheres made at 180 and we carbonize this at different temperatures. And we do this because we can vary different parameters, such as the interlayer spacing, the amount of oxygen group, the type of interconnection between your carbon atoms, closed to open porosity. And then this is just the summary of sodium ion batteries, which means that you get very different performance depending on the properties of your material. So if you look here, this one works the best. You have a very nice slope and plateau region. And then here it doesn't work. So here it doesn't work, then it works, then it doesn't work because you're actually losing your plateau capacity here. And so we've been trying to understand why. And it seems there is a sweet spot where basically you have the right oxygen atoms because you do need some defects for sodium to absorb, dissolve, and this seems to be around here, around 3.5%. You want the right interlayer spacing, and the interlayer spacing should be just a bit more than 3.6 angstroms. And you also want the right pore size distribution, but more than this, for the pore size in sodium-ion batteries, you want the right amount of pores that are closed, but you also want your connectivity to those pores to be good, which we determine using pair distribution function and solid state NMR. And based on all this characterization and tuning of our hard carbon, we realize that as you want to be for a maximum storage in this situation, where you have an interlayer spacing wide enough for intercalation, large pore to provide more storage, and sodium can access these closed pores while your electrolyte can't. So you also get a high Coulombic efficiency. And here you can have bigger pores, but if the access to these pores is closed, you can have as many pores as you want. You do need the connectivity throughout the carbon to conduct sodium and allow sodium to sit in these pores. And so again, this is another area where we've did a lot of work. It's sodium ion batteries. So if you're interested, these are just some ideas. And finally, I will just tell you very briefly the new thing that we're working on, which is making hydrogen from biomass via electrolysis. So again, in the UK scenario, there's another great ambition to go from 27 terawatts hour of hydrogen to 270 by 2050. And as I said, most of this will be gas reforming, but we need to look more and more into green hydrogen and alternatives. We need to be ambitious here. And biomass has a great potential to create hydrogen, but not via pyrolysis, but rather than electrolyzing water, you could directly electrolyze biomass. So you could partially oxidize your biomass at the anode and, for example, produce hydrogen at the cathode. And you could use this with different things. You could use HMF that you generate in the aqueous phase of hydrothermal carbon, or you could use glycerol, for example. And the advantage of doing biomass versus water electrolysis is that this potential at which biomass is oxidized is much lower than actually the potential at which you electrolyze water. So you have a reduced voltage input, and also you don't need a gas separation because you don't produce oxygen and hydrogen. So it's much easier, but you still need to separate your products. And so we've been looking at glycerol to start with, and we've been looking at platinum and platinum nickel alloys, and what we want to get from glycerol oxidation is we want to get these C-free products, which are of high value, tartanic acid, glyceric acid. And you could see if we move away from platinum and we increase the nickel into the content, so we reduce the platinum content, we can actually get the selectivity right towards more of this high value glyceric and tartanic acid products, which is quite nice. And I think I will just stop here. We're also working on making catalysts, replacing platinum from fuel cells and photoelectrocatalysis, but I won't have time to talk about this. So with this, I think I would like to thank you very much for the invitation, and would like to thank my research group. Has been a very challenging year this year, but hopefully things are going to get better. So, and also I could come to China again because I miss it. Normally I would come every year, but this wasn't possible recently. Thank you very much for the invitation.
Thank you, Magda, for your wonderful talk. And we have collected several questions from our weekend platform, and we will ask you questions half an hour later after Xiaohui's talk. So thank you very much.